Okay, 1020, we're back after a really ridiculous power outage caused by my plug coming out of the extension cord. I don't know how I'm going to stitch the first part and second part of the recording together, but I probably won't. I'll probably just throw them both up there later. When I left off, we were talking about the photoreceptors in your eye, and that is related to things I want to talk about today, although I wanted to get around to it a little later. If you quickly type into Google something like color sensitivity of the human eye, you can usually see a little chart showing you how you basically interpret color. So those cones that I was referring to before I was so rudely interrupted, they're kind of like little pixels in your eye, and they have some kind of interesting sensitivity to light. This is getting into the nitty-gritty here. One is sensitive to blue light, the other is sensitive to green light, and the third is sensitive to red light, and they overlap a little bit. You'll notice that the human eye is much more sensitive to greens and reds than it is to blues and violets. One of the sad things about not doing that spectroscopy lab together is it's really cool to try to look at the spectral lines of atoms in the violet, because when you're sitting there looking at violet emission lines, they're like ghost-like your eyes are playing tricks on you, trying to figure out if you're actually seeing them or not. Your eyes just really struggle with violet. Interestingly enough, so do CCD cameras, like the type that I'm using here to interface with you. The electromagnetic spectrum is really important to us, so we have to take some notes on this. But let me just remind you what you are taking a spectrum of. All of this stuff, oh shoot, now I'm going to load up my stupid slideshow. I'm having a bad technology day, guys, and I want to die. Okay, so here we go. Here we go. All of the different types of light are actually the same thing. Remember that light is an electromagnetic wave, and I haven't figured out how to run my flash files since they lamely deactivated it. But if you take an electron or a proton and you give one of these charged particles a wiggle, the field lines that come off of them will make a little ripple. It's a little ripple of electric field, a little ripple of charginess that comes off of your electron. You could say that it's invisible, and that's true in a way. Ironically, you can detect light, but you can't see light. Does that make any sense? Your eye can detect photons, but you can't see a photon. You can't see a ripple in the electric field any more than you could see the field between these two magnets here, right? If you take two north poles and you push them together, you can feel that there's something there, but you can't see it. Well, light is related to that invisible force field. It's a ripple or a wave in the force field. The only thing at first that makes one type of light different than any other type of light is just its wavelength. Except that's not really the whole story. Like, the only thing that makes radio waves different than visible light is the distance from crest to crest. And yet somehow, when you change the wavelength of light, you change the way it behaves and interacts with matter. That's what I'm here to teach you about today. So let's get going. Let's take some notes on the electromagnetic spectrum. I'd like to take one last little addition. I want you to add a note right here before we go forward. Because I'm going to use my proportionality terms now, because energy is inversely proportional to wavelength, that means something to those of you who speak math. And it means this. Short wavelength equals high energy for light, and long wavelength equals low energy. The longer your wavelength of light, the lower the energy of the photon. Did you guys notice my symbolic use of colors there? Those weren't just random colors I picked, were they? Who understands? Why did I choose blue and red?
So the blue blue is for magnetic field and the red for electric field.
No, no. That they did use those two colors, but that's just unfortunately a unfortunate coincidence.
Oh my God! Because the violet has a lot more energy than the red color.
Right. Red is towards the long end of the spectrum, right? And blue is towards the short end of the spectrum.
That's why ultraviolet can give you burns.
Right, and it continues past visible. So let's go ahead and let's take a note on the electromagnetic spectrum. I expect you to have this memorized for the exam, by the way. So no tricks. You need.
Can I just see the bottom of that really quick, please? I'm sorry.
Let me know when you're all set, Sabrina.
And then, H times C.
I'm so mad that this video is not going to be stitched together. That's
Wait, the short, hold on. Let me write that short.
Short wavelength.
Equals high E energy.
Yep.
And then long wavelength equals low energy. Okay, all set. Thank you.
Yep. All right. So let's take some notes on the electromagnetic spectrum. This is sort of like the periodic table of elements, except for light. Oh, I gotta get the fucking Logitech again. Oh, I had everything all perfect. I really did not have time for this nonsense. All right. In the middle of the electromagnetic spectrum, we have visible light. By the way, sometimes what these are called, the way an astronomer would talk to another astronomer, they would refer to these as regimes. No apostrophe, sorry. These are regimes of the electromagnetic spectrum, right? And a regime is like a territory or a zone. In the visible spectrum, and here what we're going to do is we're going to plot wavelength increasing to the right. And that also means that energy is increasing to the left. Okay, sorry, I smushed that. Here we have the VIV-G-your spectrum. You'll remember that's my acronym for the rainbow. Violet, indigo, blue, green. Oops, sorry. There's a reason I did B for green. Green, yellow, orange, and red. So these are the wavelengths that your eye can detect with those cones that Taryn was mentioning. Let's remember that 700 nanometers is the edge of the red end of the spectrum. 400 nanometers is the violet end of the visible spectrum. After red, there's a regime called the infrared, or sometimes just the IR. Like I said, infrared light is the type that's generated by toasters. It's also used in your television remote controls. Infrared starts around 700 nanometers, and it goes up to about, oh gosh, how do I do this here? So because we're going to change so many orders of magnitude in terms of wavelength, we constantly change the units that we're using. It's a little bit irritating. You guys remember, for instance, that a nanometer is a billionth of a meter, 10 to the minus 9. Sometimes people also use micrometers. A micrometer is a millionth of a meter. So after 700 nanometers, when you get to 1,000 nanometers, that's right around 1 micron. And people often measure wavelengths in the infrared in units of microns. And that goes up to about 1,000 microns, which is around a millimeter. In somewhere around 1 millimeter, you enter a new type of light called the radio regime. Radio wavelengths are very long wavelength, very low energy light that's produced by radio towers. You know these cell phone things that you can't get enough of? They're communicating to your local cell phone tower using radio signals. This is basically like a low-level radio transmitter. The wavelength at which your typical cell phone operates is just past infrared, just over the edge into the radio, somewhere in a few millimeters. Radio stations, radio towers. On the short end of the spectrum, short of violet, you enter a regime known as the ultraviolet. I'm just going to abbreviate it as UV because I didn't plan out my board space correctly. And ultraviolet goes from 400 nanometers down to about 10 nanometers. As Vladimir suggested to us, short wavelength ultraviolet light is the type that gives you a sunburn when you go to the beach. This light you can't detect with your eye, but it's very damaging to skin cells. Butchers often have ultraviolet lights right in their butcher shop because they can kill and zap pathogens and parameciums that come from raw meat right there on their butcher table. In fact, people are actually starting to use ultraviolet lamps to kill coronavirus in the air. They're obviously very expensive, but in certain hospitals where they know they're going to be treating coronavirus patients and there's just virus particles floating in the air, they just flood it with ultraviolet light that you can't even see. And that short wavelength UV light just zaps and completely destroys the organisms.
That's what my mom did when I used to be younger. We had like a small, but well, actually quite powerful ultraviolet lamp. So when like I would get sick, maybe like once in 3 days, maybe she'd just like, all right, get out of the room. She would turn it on, and then when you walk back in, it smells kind of weird after the lamp worked.
It might be that you know probably why it smells weird. It's probably that the ultraviolet photons are breaking down the oxygen molecules and turning them into ozone, and you're smelling a little trace of ozone in the air. I bet that's what was going on there. Yeah, sometimes they use ultraviolet wands now to kind of kill bacteria. If you go even shorter than ultraviolet, the energy keeps going up, and the photons get smaller and smaller and smaller and more deadly. So, of course, X-rays are really useful. That's the next band, the X-ray regime. Usually X-rays are so small that they can actually pass through the empty space of cells. They use them in medical imaging because the X-rays will pass right through the fleshy parts of your body, but only bounce back when they hit the more dense bone. Unfortunately, these things can cause cancer and mutate you. So you have a very limited amount of exposure to X-rays, or that one tries to limit their exposure to X-rays. It goes from a 10 nanometers at the top down to 1/100th. I don't know if you guys can read this. I didn't plan this out so good. 1/100th of a nanometer is where X-rays bottom out. And then the very shortest wavelength of light, you're going to see me use a gamma symbol there, and I'll just bring it down here. These are called gamma rays. Gamma rays are the kind of light you hope you never come in contact with, because there's really only one way to produce such short and high energy photons, and that's through nuclear reactions. Nuclear bombs, nuclear reactors that produce energy. This is the kind of shit that turns you into a teenage mutant ninja turtle, okay? You get exposed with this, it basically like, it's like going into your DNA and taking random snips out of the DNA and gluing them back together. You know, it'd be like the equivalent of looking at the source code for Microsoft Word and then mashing on the keyboard and hoping that something good is going to happen. You know,
this is super left field, but wasn't like the Incredible Hulk like the storyline? Isn't that what happened to him?
Yeah.
Right. So here's where this comes from.
Okay.
In nature, all of our innovations in design for human organisms, for octopi, for pterodactyls that fly, whatever the hell it is, they all come over time through random advantageous mutations. For every 1 million little screw ups that makes your body not work right, every now and then there'll be a random good one that's so beneficial that you capture more eggs, or you have more mates or something like this in nature. So over time, over hundreds of millions of years, these one-off random mutations help. If you flood your body with gamma rays, you're basically going into the DNA of your body and you're snipping little pieces out and gluing it back together in random ways. Now, 99.999% of the time, that's just going to result in cancer or something bad. That's not going to, your body's not going to be producing the things it wants. But there's always the possibility, even though it's slight, that if you flooded your body with gamma rays, you could get some of these weird advantageous mutations, some
Yeah, but
superpowers.
it's not going to be like they represented in movies, right? Because it's
Yeah,
well,
this is a plot device in movies, because they say, well, you don't know, it couldn't happen, right? One of the things that I read that was kind of an eye opener for me, it might be in my shelf here somewhere. I read this first person account of living through the atomic bomb in Nagasaki. I think it was Nagasaki, by Abuse Masuji. He was a Japanese writer who wrote this book called Black Rain. I got to tell you guys, it's a real bum out. It's profound, but he survived the blast. The people that were closest to the blast wave, if you didn't get vaporized, you avoided the wall of gamma rays that just spilled out from the city into the surrounding towns. And so he was kind of weirdly close to the blast, but not close enough to just get vaporized. But he kind of, somehow the wall of gamma rays got past him, and all of his friends, his sister, and his brothers, they all got hit with this huge gamma ray blast. And of course, some very, very bad and unpleasant things happened to them all. They all started getting these horrific mutations. But I remember one part of the book where he walked by a koi pond, and the grass had just started growing at this hyper accelerated rate. And he went by like 2 days in a row, and the grass had grown like a meter tall, just because it had gone through some weird genetic mutation.
it was such. Wait, can you repeat that part? You said the grass started to grow at a very accelerated rate.
Yeah, like he went by this koi pond that he went by every day, and between one day and the next, the grass had grown like an extraordinary degree. Like it had gone through some genetic mutation that caused its growth to accelerate, and it was a quasi, I don't know if you'd say beneficial or not. I don't know what I don't know what's good for grass, but the point is, things were weird, things were funky. He saw one of those potentially Incredible Hulk. I mean, that is kind of Incredible Hulk, right? You grow and you're green. So
Wait, I have a question.
Yeah.
So what's the name of the disease when you are, well, not technically poisoned?
I mean, radiation sickness.
Oh, that's what it's called?
Yeah, it's called radiation sickness. And it usually does not turn out well for you. Like, that's why you have to be extremely careful with this stuff. However, it's probabilistic. Man, there's so much I could say about this. Learning about the different regimes of the electromagnetic spectrum is really interesting. I could tell you a million cool stories about each one of these. Kind of don't have time to do it, although maybe I'll indulge a little. Here's the point for perspective of astronomy. So hear me out on this. All this different type of light, it only differs from one another by wavelength, right? So one photon has a long wavelength, the other has a short wavelength, but they're all electromagnetic ripples. And yet, they each interact with matter in their own unique way. And you can kind of get a sense of that, right? Like radio waves are used to, tune into your favorite radio or TV station. This is the type of light you can see. This is Sunburn City. This is Teenage Mutant Ninja Turtle City. All right, so they all behave in different ways, but stars and different parts of our galaxy emit light at different parts of the electromagnetic spectrum. And what you got the other day when we were looking at the emission lines of visible light was just a little taste of how you can analyze all of these different types of light to learn about the physics of the material that is emitting that light. For instance, if I could call up one of my slideshows here, let's just look at hold on, where are you guys? Let's just look at a field of stars, for instance, right? when we try to look at stars, field of stars, star field, okay. When we're out there looking at something awesome, like let's take this globular cluster here, okay? This is a star cluster. I think this is a globular cluster. All of those stars are little single mathematical points of light. They're too far away for us to see their surfaces, to see the cool solar flares that are blasting off the top of them. We can't actually see any details with our eyes, even with telescopes. But each of these little pinpricks of light sends a beam of rays to us, which we can break apart and we can analyze, not only at the visible regime, but we can study those pinpricks of light in the infrared, in the ultraviolet, in the X-rays. And part of the lesson for today is learning how we can use those different bands to study different parts of the star. You can figure out everything from what its chemical composition is, to how much it rotates, to whether or not it's oscillating. There's just no end to it.
I have one more quick question. So let's say I don't know if this is like if anybody's figured this out or not, but
Okay.
if a star were to I don't know, explode, I don't know what's that called, or if we can even see that
Usually
far or guess, would
supernova.
that could that emit like some kind of like gamma rays or stuff like that?
Yeah, I don't think we studied Tycho Brahe in this class, but he's an old-timey time astronomer that saw the birth of a star. Today, there's a telescope that we have which just looks at X-rays. It's called the Chandra X-ray Observatory. Let's look at a picture. We have a number of different space-based telescopes, which are really awesome at seeing deep into space. One of them, the Chandra X-ray Observatory, here's a little rendering of it. This telescope is only designed to look in one band of the EM spectrum, X-rays. And it turns out that what X-rays are really good at, Nick, are exactly what you're talking about. Super, super high temperature plasma tends to emit X-rays. So when a star explodes and it shreds itself, the gas gets superheated and all the electrons get ripped off and it just starts glowing at X-ray wavelengths. So let's look at a picture of what's called Tycho's supernova. This supernova went off in 1572. So, okay, it sounds like, 500 years ago, but that's a short time cosmically speaking. This is what it looks like. The best image we have of it is in the X-ray part of the electromagnetic spectrum. And this is the Chandra X-ray Observatory's picture of it. Nick, what you're literally seeing is a bubble of hot shredded gas expanding outwards at super high velocities. Now, if you looked at this same object with visible light, you'd see nothing. You'd see black darkness because it's so faint and so far away in terms of visible light, you can't see it. But if we instead put on our X-ray specs, now you can see the bubble of super hot ionized gas. So absolutely. So what you said is true. Yeah, and this is just one example of a million different examples I have for you.
I have 2 questions.
Okay.
Regarding the spectrum. How far does do the gamma rays go?
That's such an interesting question.
Because can they get just infinitesimally small, or there's like some finite?
Okay, shit gets really. I'm every now and then someone asks that question. It's one of my favorite questions. So let's first ask about it the other way. Suppose you go to radio.
Yeah, the other way too. Yeah. And what about the microwaves too?
Microwaves, sometimes people include microwave as its own band here. Microwaves exist between infrared and radio. So real serious professional astronomers will distinguish between the infrared, the microwave, and the radio band. But I think 6 regimes are enough for you guys to memorize. And there's some weird overlap. Now, Vladimir, to quickly answer that question, because it's cool and it's relevant, radio waves, as you get longer and longer wavelength, also become lower and lower energy. So eventually you just kind of stretch the wavelength out so much that the energy of the photon kind of disappears and it peters out to nothingness. That explains the long end of the spectrum. Here's where shit gets weird on the short end. For gamma rays, you keep making the photons shorter and shorter wavelengths, and you start smushing. I'm not doing a good job of this here, but the wavelengths get closer and closer together and more smushed, and the energy of the photon gets higher and higher and higher. Eventually, the photons actually stop acting like photons, and they can pretty much literally start turning into electrons and protons. So like those photons become so much particle-like that they eventually actually start transmuting into physical particles of
Wait,
matter.
that actually, oh, okay, that's so way over my head. But like, photons are supposed to be massless. So like, as you
Right.
compress, oh, that's why it's connects.
Well, hold
So
on, but
when they
hold
gain
on.
enough energy, mass is potential
I'm giving
energy.
you a simplified version, but we're going to talk about this at a later date. So
Okay.
all of these cool things we're going to explore. Right
So
now-
since I'm sorry.
give
So
it to
since since all the protons are going like really crazy, is that what is directly responsible for all of like the genetic mutations that it causes?
Oh, I see. So hold on. When you said protons, I think you meant to say photons, right?
Oh yes, photons.
Right.
Sorry.
Gamma rays can cause genetic mutations, but I think all right. So this is a question you'd probably want to ask your bio teacher more than me, but I think that no, you can cause genetic mutations through other things as well. For instance, you could drink a lot of booze with some sulfur impurities in it, and some chemical reaction, a little sulfur ion or something, a free radical as they call them, could go and attach itself to your DNA and snip a piece out. So the quick answer to your question is, Taryn, is it could be photons doing it, but it could also be chemicals causing the mutations. Now, the idea is that, from what I remember from my bio lessons, you've got your DNA strand, and there's a little molecule that actually travels up and down, kind of like a quality control technician, and it looks for errors, and if it finds errors in the DNA, it auto repairs them. The reason why smoking is so bad, and getting hit with a blast of gamma rays is bad. By the way, smoking is a very high temperature gas that releases X-rays into your lungs, and so that also causes genetic mutations. What happens is, if you keep hitting the DNA with tons and tons of photons, you keep creating more imperfections faster than the little molecule can go up and down and repair it. And eventually the molecule just gets overwhelmed and it just says, fuck it, I'm gonna let some of the errors stand, something like that. But Taryn, it doesn't have to be
I also had a
photons.
question.
Yeah.
I had another question from earlier. I just didn't get to answer ask it. I know that during, like, if you get an X-ray, they put like a little weighted pad on you. What exactly is inside of that?
Lead.
Blood.
Yeah. So it turns out that
Oh, okay.
lead is a metal that's one of the densest metals in the periodic table of elements. And so what happens, Taryn, is the atoms are so densely packed together in lead that they block a much higher fraction of the X-rays than, say, a piece of wood would. If you hold a piece of wood up to X-rays, maybe 60% of the X-rays will leak through the wood molecules. But with lead, it might stop 85%. It's not foolproof. Some of those X-rays are still getting in there, and I don't know how else to say it. The first place they put it is they put it over your genitals, because they don't want any mutations to be related to reproduction. That's the first thing they do. And lead is going to stop a higher fraction of those photons. A few will still leak through, but they're just taking the most readily available, densest substance they have that will block the greatest fraction of X-rays. And it's statistical. It's not perfect, but like, for instance, if lead wasn't available, we would probably use some other dense metal, like steel. I'm guessing steel might be better than a piece of wood. I'm guessing a piece of wood would be better than a piece of cloth. But lead is a very effective absorber. Radioactive samples, they often put in lead boxes because they shield you from particle radiation as well.
Okay, thank
I'm
you.
going to be teaching you guys more about this stuff as time goes on.
Do you have any more time to answer, or you have to move on?
Let's move on for now, but I bet you sooner or later one of these subjects is going to come up. But there's a couple of modules I need to do for our homework, and I'm getting a little scared. let's talk about some other aspects of light. I need to talk about power. This is something we haven't discussed yet. How bright is my light source? And then I want to bring it into play with temperature and stuff like that. So let's just start with this bulb here. The other day, okay, there we go. All right. So this is a bulb that I like to use sometimes for our demo purposes. This one's very bright. But this is a little 40-watt appliance bulb. I like them because they're clear, and there's a little piece of metal that glows in there. That's the incandescent filament. I'm not going to try to plug this in because I've already had one power outage today. But let's imagine we plug this thing in and we get that little filament in there to start shining. When a light bulb generates light, so let's draw a picture of this here. So here's my little 40-watt light bulb. There's a little filament. And when I send a current of electricity through it, the metal inside heats up and it begins to glow in all directions. So white light begins to shine in every single direction. When we're dealing with beams of white light, you guys remember that we did this problem in our homework last week, and you found something like 10 to the power of 20 photons per second were streaming out of this bulb, right? Like a crazy high number every second. So it gets a little weird to try to analyze the light in terms of the individual photons and trying to calculate the energy of each photon. You can't do it. There's just too many of them. So instead, you think about light just shining out in all directions. You cannot talk about the energy coming out of this bulb because energy is constantly streaming out of the bulb. As soon as you take the bulb out and you plug it in and you turn it on, light starts to shine out. But just like water molecules flowing past you in a river, the water just keeps flowing past and flowing past. So it doesn't make sense to talk about the energy emitted from the bulb because energy is constantly streaming out of the bulb. Instead, it makes sense to talk about a different quantity called power. Power, in a physics sense, is energy per unit time. And what power is a measure of? It's a measure of energy flow. In fact, we have devices that we use to sometimes measure the energy flow coming from a bulb. Let me show you this weird device that you've probably never heard about before. It's called an integrating sphere. And it's kind of like a light detector that's in the form of a three-dimensional sphere. They've got a little light socket in there, and you can plug in a standard Edison lamp. You close it up, you turn on your light bulb, and this computer just starts to capture the photons that are coming out of the bulb. Now, you can choose how you want to measure this energy flow. First of all, let's see if you guys remember things. What are MKS units of energy?
Watts.
Hold on. We're talking about energy.
Joules.
Right.
Stupid.
MKS units of energy are joules. What are MKS units of time?
Seconds.
Seconds. Thanks, Andrew. It is the joule per second that we define as a watt. A watt is the MKS unit of power, of energy flow. And so we say 1 watt is equal to 1 joule per second. Uh-oh, the dogs are freaking out. Whose dogs are going nuts? Is that Tegan?
Those are mine. Sorry.
Those guys are always going crazy, huh? I grew up with a
Yeah.
couple of dogs, and my household sounded just like that as a kid. Okay. Power can be used in any abstract way because energy takes a lot of different forms. For instance, we could talk about the wattage of a light bulb. That light bulb that I just showed you was a 40-watt bulb. I could also talk about the wattage of a guitar amplifier, right? Like I've got these crazy dual 15 cabs in my music studio, and they pump out 1,500 watts per cabinet. That would just, that can make a polar bear go deaf. So those are powerful speakers. And when they talk about 1,500 watts, they're kind of talking about the power of the electricity they use, how much energy per time electricity, but that does translate out into the power of the waveform as well. When we talk about light, there's a specific term that's the same as power, but we reserve it for light only. It's called luminosity. Luminosity is the power of light. So I don't want this to be confused in any way. Luminosity and power mean the same thing. But you would never talk about the luminosity of a hairdryer, or you'd never talk about the luminosity of a guitar amplifier, because they don't pump out light. You could, on the other hand, talk about the luminosity of a bulb, or you could talk about the luminosity of a star or anything else that glows. So you're going to mostly hear me use the term luminosity rather than power. Here's the thing about luminosity. Luminosity, in most cases, is usually a fixed property of a glowy thing. So if you have a glowy thing, like a bulb or a star or a glowworm, usually its luminosity is constant. And let's give you a couple of different examples. I'm going to erase this up here.
So like laptops are measured in nits, right?
In what?
The brightness of laptop screens is measured.
So this is where we're going. We have to talk about brightness. Brightness is a different thing, okay?
Oh, right.
But bear with me, Vladimir. You'll see what I'm talking about in a second. The luminosity of a bulb could be 100 watts. That's what the standard old-fashioned Edison light bulb was. The luminosity of the sun, which I'm going to abbreviate in the future as an L with a little circle dot in it, it has a fixed value of 4 times 10 to the 26 watts, which is an incredibly intense amount of energy. Now, the entire power consumption of the United States, so let's look at a kind of cool picture from NASA here. I love this picture of United States at night. These types of pictures are often used by astronomers to show people the effects of light pollution. They're also just kind of beautiful. Let's see if I can, it keeps telling me my internet connection is unstable. You know what? It's probably because I'm streaming this NASA thing. Let me hit pause on YouTube. It just occurred to me that my streaming of the Perseverance landing in the background was probably competing with my my transmission to you guys, which is not good. Look at this totally cool picture here. Wait, we want the super high res version. Yeah, that's great. So one of the reasons why Rhode Island is one of the worst places in the world to do astronomy is because look at all of the light that's competing with the background sky. New York City, Providence, Boston, they're some of the most light polluted areas on Earth. The entire United States, if you think about its energy consumption, it uses energy for powering the street lamps, for the Nintendos, for the nuclear power plants, whatever. Well, I guess they generate energy. The entire energy consumption of the United States, and we can talk about its power requirements for the entire United States of America, is 1 times 10 to the 20 joules per year. So we use about 10 to the power of 20 joules per year. Compare that to the luminosity output of the sun, 4 times 10 to the 26 watts. Wouldn't it be cool if we could surround the entire sun with a gigantic integrating sphere In science fiction, they refer to this as a Dyson sphere, a huge solar panel that would cover the entire star, and we could capture all the photons emitted from the star and, like giant space ticks, suck the energy off of our own sun and use it to our advantage. Such a thing could harness an immense amount of energy. Let's just play a little game here. Let's say we could have a Dyson sphere and we could just collect total sunlight, all the beams of light coming off the sun for 1 second. I'm going to ask you guys the following question. Suppose I could capture all light from the sun in all directions for 1 second. The question is, how much energy would I get? This is actually supposed to be an easy question. Does anyone think they can answer it?
I think I can.
Give it a whack. You shouldn't have to do any complicated math. You should just have to think about it.
So that would last. So the energy you would capture in 1 second from the sun would last you to power
No. I just
the entire North America for a year.
Vladimir, pew, you're going off on a side tangent here. I'm asking a direct, specific question. I want a direct, specific answer. How much energy would you gather if you captured 1 second of total sunlight? Don't start telling me about times and other weird stuff. I want to know a quantity of energy.
4 times 10 to the 26th joules.
Excellent. Very good. Vladimir understands the difference between power and energy. Let's go through how he did it. 4 times 10 to the 26 watts is the same thing as saying 4 times 10 to the 26 joules per second. And those joules are streaming out in all directions. He multiplied it by 1 second, and he got a total energy of 4 times 10 to the 26 joules. Vladimir, that was a test to see if you guys could understand the difference between watts and joules, and you passed it perfectly. I'm very impressed. All right, now we can answer the question that you were about to say. How long? Clearly, that's more energy than the United States uses in an entire year. How many years could I power all of the United States energy needs from that 1 second of total sunlight? Who knows how to do that? So the question is, how long can I power the USA with that? Oh God, this day is getting away from me. The answer is you divide this energy by that energy per year. 4 times 10 to the 26 joules divided by 1 times 10 to the 20 joules per year. Okay, do the math and do the units. You guys know how to divide that in your head, right?
Yeah.
Well, then do it.
I don't know. I mean, it's just, I don't know. I didn't want to kind of take the opportunity for others to answer.
I mean, I guess one thought, let me tell you where I'm at. I'm like, can these guys even divide two numbers in scientific notation in their head? That's what I'm wondering. I don't know if you have that skill or not. Nia, do you know how to do it?
Yeah. You can last for over 4 years and you'll have like 4 million joules left.
No.
No?
Well, your number's good, but your units are bad. Okay, look, we got to work through this slow. 4 divided by 1 gives you 4.
Oh, I got it. It's 4 times 10 to the 6 years.
That's right.
Oh, wow.
Joules cancel. So
Uh-huh.
26 minus 20 is 6. You could power all of the US's energy needs for
5 million
4
years.
million years from 1 second of total sunlight. That's insane, right? Why, Jesus, man, why haven't we made one of these Dyson spheres? I think I like the sound of that.
I mean, we probably don't have enough whatever material is needed, right? Like the
Right, okay,
entire
so that's one issue. But here's another way to think about that same issue, Vladimir. If we don't have the material to cover the sun, we can't get all of those photons, right? We can only get a small fraction of the photons. Most of that light just spills pointlessly into outer space so that aliens in a distant solar system can see our sun as a little twinkling star in their sky. So most of those photons just go into lighting up the skies of alien worlds. We do get to capture some of that sunlight, but only the fraction that makes it to us. And that's a different quantity called brightness. And you guys need to learn the difference. There's the luminosity, that's how much light is emitted by the object. And then there's how much you can capture at your detector or planet some distance away. Let me define a new quantity now.
What if all the highly advanced aliens just created a Dyson sphere, and that's why we think we are alone, just because we cannot sense the light coming from their stars?
There's a name for that. It's called I think that's related to the Fermi Paradox, which is if there's so many aliens out there, shouldn't some of them be intelligent enough to be traveling around in spaceships? Why haven't we seen them yet? And that's a question that people ask all the time.
What if they think we're just way too dumb?
Well, it's the distance. Distances are really immense in space. So even if you are a really intelligent alien race, it's still just hard to get from one star to another. Okay, let's talk about a quantity called brightness. Brightness is defined as the luminosity divided by some unit area, and the area is usually the area of your detector. A detector could be your eye, it could be a camera, it could be a telescope. In a way, you could even talk about the area as being the area of a planet. The area is a little bit loosey-goosey, okay? And usually what happens is you have some light source. It could be a bulb or it could be a star. And that bulb has some luminosity, which, as you know, is pumping out light in all directions. But when you're interested in the brightness, you're interested in some cone of light that's being splashed 3D art skills over some area of detector like that, okay? So this is the brightness B here. If you think about the units of brightness, the units are watts, because that's MKS luminosity, per square meter. Now, in most cases that we study in our class, we're going to be studying a situation that looks a little bit more like this. There's a star which pumps out some luminosity, and as the light travels, the light is being spread over a bigger and bigger and bigger sphere. And the nice things about spheres is that we always know their surface area is 4 times pi times the radius squared. And this allows us to sort of derive a very important formula called the inverse square law. The inverse square law tells you what the brightness of a light source is, how much you will detect at some distance away. And it has two versions. One is brightness is luminosity over 4 pi r squared. Or another version could be considered the brightness is the luminosity over 4 pi d squared. And actually, both of these formulas are the same thing, but the way you can apply it is different. And I'm going to have to kind of give you some concrete examples. Usually you use this formula to find the brightness at the surface of a star. And usually you use this one to find the brightness of a star on your sky. Let me draw the cartoon picture up here. Hopefully I'm not going too fast for you guys. In fact, I'll draw a cartoon picture for each one of these. For the first version of the formula, you have a star. The star has some radius r. And when you calculate the brightness, you're basically asking how many watts per square meter are being generated at the surface of your star or glowing object. In this case, it's slightly different. This is usually a situation where you have a star that's pumping out light, and you think of yourself as being really far away on Earth, and the light from the star is being spread out over a huge sphere whose radius is r, but we really call it d, the distance from Earth to the star. And
Oh,
here,
that's why I was confused. I was like, why diameter squared?
it's not diameter. Little d is usually used for distance. In both cases, you're asking about the light that's coming on the surface of a sphere, but this is the actual surface of the star, and this is just how much. In fact, the panel is really centered on Earth because you're here, the observer. You're really asking, how much light am I getting on Earth? Some distance d away from the star. We'll probably try examples of this in our labs, or sorry, in our homework today. Guys, I've really messed up this day in a big time way. You also helped me mess it up by asking me all these cool questions, which I like because that means you're engaged with the material and it makes my day more fun. But unfortunately, we got carried away today. Also, leaving my laptop unplugged was a stupid bonehead move.
Professor,
Yeah.
I have to leave the lecture a little bit early.
Okay. Just make sure.
I have an appointment I have to go to. I'll watch the rest of the lecture when you upload it.
That's fine, Nick. Yeah. In fact, you might even want to watch last semester's at the rate I'm going.
Okay.
But,
All right.
I will have this uploaded eventually, though. Okay. So
All right.
see what else
Awesome.
happens.
The
All right,
bottom.
bye.
Thank you.
Sure. Okay, I'm gonna just kind of squeeze in a couple more things with the hardly 9 minutes I have left. It's not gonna be pretty.
I can't see the bottom of the thing. Thank you.
Let me know when you're all set, Andrew.
I'm all set.
All right.
Is this energy right here on the second diagram? Or brightness? Is it E or B?
Oh, I originally put E because that's the Earth. Like, here's the Earth. You are here. And you're looking at some star in your sky, which is 20 light years away. And you're trying to figure out how bright the star is on your sky. At this point, what I should do is I should do a sample problem with the inverse square law, but I don't have time. I have to do 2 more little modules for our homework. So like I said, today's just going to be ugly in a few ways. Just take some notes with me, okay? Anyways, the brightness is coming off the panel here. So if you want, you can put the B there. Does that help? Probably not.
Oh, yeah, I wasn't sure if you see my face. I was nodding, but yeah, that does.
I can only see about 5 of you at a time, so you were. Okay, good. All right, let's talk about stuff that we intuitively learned in our labs on Tuesday. Light can take a variety of different forms, and I want to show you a little cartoon here. we're going to learn a very important module called Kirchhoff's laws of radiation. There are three types of spectra that you find when you break apart a beam of light. And you can imagine breaking apart all kinds of light. I could break apart light from a star, light from a light bulb. I could break apart the light on my phone. I could break apart the light from a glowworm, whatever. When you break light apart into spectra, you tend to find one of three types of spectrum. You either find a kind of perfect rainbow, and this is all going to be described in the visible spectrum, but this carries over to other wavelengths as well. So there's a continuous spectrum, which is a rainbow. There's an emission line spectrum, which you guys actually drew a bunch of on Tuesday. And then I tried to show you this one on the sky, and I had kind of mixed results. You could barely see the lines, but there's this type of spectrum called an absorption line spectrum. And there was a famous, quite evil-looking scientist named Gustav Kirkhoff. I just say this because his picture is very, wait, where am I here? If you look this guy up, Gustav Kirkhoff.
What does he have, like an intense face?
Yeah, I want to show it to you just because I have to put this into my slideshow at some point, but he just looks like a serious, 18th century mad scientist. This Prussian scientist, this impressive fellow named Gustav Kirkhoff, he did many cool discoveries. Is that a bolo tie that he's wearing? I like this man's style here, okay? Anyways, let's bring back this look, 2021, okay? Gustav Kirkhoff, legendary Prussian scientist, working in the 1800s and early 1900s, basically he was a collaborator with Bunsen, who invented the Bunsen burner. And once they invented the Bunsen burner, which had a colorless flame, they just started taking salts of every damned imaginable compound they could find and burning them and analyzing the light to see what would happen. And after Gustav Kirkhoff had just gone, basically he got one of these things. He got a spectroscope. And just like any of us would if we were playing with this thing, I'll tell you what I did the first time I got one of these. I just went around my room, and every single thing that glowed light, I would just look at the spectrum of it, right? So he did this for all these different types of light sources, and he found that there were basically only three types of spectra produced: continuous, emission, or absorption. But what's important is he pegged each spectrum to the type of material that emitted that spectrum. So in other words, if he saw a rainbow, it told him something about the thing that was emitting the light without him having to see it. And he invented what are called Kirchhoff's three laws of radiation. Every astronomy student needs to learn these. They're just as important as Kepler's laws. So Kirchhoff's laws of radiation. And these are going to be really important for us when we analyze starlight going forward. The first is called the law of blackbodies. And blackbody is an archaic term for a hot, dense, glowing thing. And it goes
That doesn't make sense.
Well, the idea behind a blackbody is most matter, even matter that is dark and black, doesn't absorb 100% of the light that it emits. So my dark velvet jacket does absorb quite a bit of light. You can see on this camera, you don't see much off, but if you were standing here in the room with me, you'd be able to see some highlights. This probably reflects, I'm guessing, maybe 5 to 10% of the radiation that hits it. So it's not perfectly black. Black bodies are an ideal substance that is perfectly black, and it only emits light because of its temperature. But let me explain that in a second. The law of black bodies says a hot, dense solid produces a continuous spectrum. So in his first law, he's telling us that hot, dense, solid things, when they get warm, they produce a continuous spectrum. You guys remember that continuous spectrum is code for the rainbow. So what you used to call a rainbow, from now on, we're going to call continuous spectrum. One of the ideas behind black bodies is these objects glow due to their temperature alone. And here's an important part, not their chemical composition. And literally what that means is a glowing piece of metal in a forge will glow exactly the same as a flaming piece of dog poo. All that matters is the temperature, not whether it's made of metal or dog poo. Both of those things are solids, and both of those things will glow if you heat them up enough, okay? Doesn't matter if you're dog poo or metal, you glow, your light depends upon temperature only. That's what a black body is. Okay. The next two laws do depend upon your chemical composition. The law of emission is going to explain how we got those emission lines. Remember when I put those gas tubes inside here and I made them glow like neon colors and stuff? Those types of materials are glowing due to the law of emission. And it goes like this. A hot, thin gas produces an emission line spectrum. So a hot, thin gas produces an emission line spectrum. And I've shown you a couple of different examples of this.
Thin meaning low pressure?
Low density. But those two things go together by the ideal gas law. So you could say it that way. Let me show you a couple of different examples. In our labs this week, you got to see a number of different emission line spectra. I showed you hydrogen, I showed you neon and mercury and helium. I didn't show you sodium. I didn't happen to have sodium, but sodium's famous for having only a pair of double yellow lines as its emission line spectrum. Emission spectra do depend upon the chemical composition. Each element produces a completely unique emission line spectrum. Your book actually calls it a chemical fingerprint, but it's better to think of it as a fingerprint in light. In fact, someone actually went as far, let me go to slide 5, it's somewhere around there. Someone went as far as to redo the entire periodic table of the elements, all as different emission line spectra. So here, it shows you the emission line spectra of all the different elements in the periodic table, showing you no two element is like. Think about why that's so important. If I can find these lines being emitted from starlight, I know that that element is present in the star without having to travel there, right? This is how I know that the material that the stars are made out of is not fundamentally different than the materials on Earth. Like if we were like, you know, doing bong rips in a basement on a beanbag somewhere, you could start going, bro, how do you know that like the reality out there in the stars is like even the same as our reality? You can't even comprehend that because it could be like so many different things that your pea-brain, pusillanimous mind can understand. And I would say, nope, false, because I can take a spectrum of those stars and find out it's made of the same stuff. Sorry.
Wait, isn't it hard to separate the spectra though? Because like stars are made up of, I would say, like more than two elements. So when all those spectra mix, how do you separate them?
By being a badass. That's how, okay? And this is what astronomers do. The answer to that question is when you actually start, you know, it's like the difference between be like, oh, I think I could make, you know, that sculpture, that Rodin sculpture, and then sitting there with the clay and doing it. That's where the art begins, my friend. And I know because I've got this really badass spectroscope over there. Maybe I'll show it to you. And I've been attaching it to the telescope and taking the spectrum of star. And it's like long, chilly nights at the telescope with me doing this while taking pictures of stars in the dark or fighting off mosquitoes. Who knows? Maybe one of you guys will be nutty enough to come along with me. And I've had students come out and do this stuff, but it's long, hard work for little tiny gains. So it's when you ask that, Vladimir, I just visions of cold, terrified nights in the dark just flash before my eyes. But maybe I'll teach. But then again, if you're getting paid $200K a year to analyze the compositions of stars, well, shit, that's better than
One
flipping a
does not
burger, right?
mind does not mind getting freezing.
Yeah, but you know, that's kind of what one thing I like about astronomy is it's kind of like there's this kind of Shackleton Arctic exploration thing going on where you have to get all bundled up and battle the elements of nature. It's cool. Let's talk about that third type. Oh, one more thing. Where would I encounter these emission line spectra in nature? You've already seen an example of that if you remember the, wait for it, Rosette Nebula. You'll remember I showed you this cool astronomy picture of the day of the Rosette Nebula. Do you guys remember what's responsible for that beautiful red color?
Hydrogen cloud.
It's high. So this is hydrogen gas, correct?
Ah,
Even
what kind?
bonus points if you remember the name of the emission line.
Oh wait, alpha, hydrogen alpha.
Hydrogen alpha, right? So for instance, if we were to look at the spectrum of hydrogen, here's hydrogen alpha right here. If you pass that nebula light through your spectroscope, you would see nothing except for that one pure red line right at 656 nanometers. That's all the spectrum of the Rosette Nebula would look like. Now, you might ask me, why aren't those lines there? That's a great question, but I don't want to answer that just yet, okay? Now, take a look below here, and you can see an example of what's called an absorption line spectrum. An absorption line spectrum is when you get a rainbow, but instead of emitting light at these particular wavelengths, you find that those particular wavelengths are missing from the spectrum. And you might be able to guess what's going on. Instead of having an electron drop from a high orbit down to a low orbit and emitting a photon, in this case, the situation happens in reverse. You have an electron which is sitting at a low orbit, a photon of just the right wavelength and energy comes along, the electron grabs it and eats it and uses it to jump up to a higher energy state. This, of course, will remove the photon from the spectrum, resulting in a dark spot where the line should be. This is called an absorption line spectrum, and these are actually going to be the most useful to us in our class. Let's take
Professor.
Yep.
Oh, I was gonna say if you could not erase two because I have to write it, but I think you have enough room.
Yep, good call. The third is the law of absorption. And that's a cold, thin gas. The gas needs to be cold so that the electrons are in the lower energy state. And here's where it gets weird. A cold, thin gas in front of a black body produces an absorption line spectrum. Now that Kirchhoff has hooked us up, we can analyze the spectrum of any different type of light source, and we can know that whether it's a dense solid, we can know whether it's a thin gas, or we can know whether it's a cold gas with a solid glowing object behind it. And it won't be obvious how this is useful to you just yet, but as we go forward, you will see me using these laws all the damn time. You must memorize these. I will test you on them. I consider this wicked important stuff. Now, before we do our homework, I need to squeeze in two formulas. I'm not going to do sample problems because I totally don't have time for that. But there are two formulas that we need for our homeworks today, which are related to black bodies. So once you guys have these notes, I'm going to slap them on the board, and then we'll take our tea break. But I need to slap them formulas up on the board. Sorry, today got a little wacky. Was it Kiana? Kiana, how you doing? You still writing?
Yeah, I'm just writing the last line of number 3.
All right, let me know when you're good, and I'll check on everyone else. All right, are we good? Can I erase? All right. Any objectors? I want to talk about I just want to write down two formulas, but a moment ago, I suggested to you guys comically that a flaming piece of dog poo could be a black body. And the funny thing is, I wasn't really lying to you. That a flaming piece of dog poo would be considered a black body, but that's not the most ideal picture of a black body. Here's what would be. Let's picture a steel ingot in a forge. And there's a few different pictures of this on the internet, but one that I kind of like just for its mundane boringness. Where is it? There's one that this one would be okay. Oh, I like this one. I just really like how boring this picture is. It really gets the point across. Here's just a boring little lump of metal. It's just a block of steel or something. And they put it into a forge and they heated it up and they raised its temperature. And lo and behold, once this dense solid becomes hot enough, it will begin to glow. If you were to pass that orangey looking light through a prism, it would actually look like a pure rainbow. A pure rainbow would come out, I swear to goodness. Now, this is an idea of a black body. It's just some solid thing that's glowing. And the light doesn't actually depend upon whether it's steel or whether it's coal or whatever. It's just going to kind of give off a rainbow. But the rainbow itself does depend upon temperature. And let's think about what happens when you heat up a metal object in fire. You're going to notice two different effects. And this little cartoon kind of shows you what's going on. So you take something like an iron poker and you put it into a fireplace. And at first, when it's cold at room temperature, it doesn't really appear to be glowing. It's just a cold black piece of metal. When you put it into the fire, you'll notice that eventually it starts to glow kind of a dull orange, and then it gets kind of red hot. And then if you keep heating it up, eventually the metal will glow white. So the color is changing and the brightness of the light is changing. You can't get an iron poker any warmer than that in a typical fireplace. But in industrial applications, they use a blast furnace where they pump air and oxygen into it to make the temperature higher and higher. If you put a piece of metal into a blast furnace, you could get it so hot that it would actually change to a pale blue color. And then it would look very cool. It would look like a kind of glowing blue metal. That tells us that black bodies have two things going on, and you're going to need them for your homework today. So I just kind of wanted to get them on the board. As I heat a black body, I get two effects that I just described to you in cartoon form. And we're going to kind of write them down in just a simple way with a formula for each of them. The first effect is more temperature equals more light emitted. Your object will become brighter and brighter in terms of its watts per square meter. And this is encapsulated by something called the Stefan Boltzmann Law. Let me try the spelling on that again. Boltzmann Law. The Stefan Boltzmann Law basically tells you if you have a lumpy piece of metal that's glowing, it's going to tell you the brightness that's coming off of a little square panel of your glowing object. And the formula is the brightness of your black body is a number called the Stefan Boltzmann constant times temperature to the fourth power. Now, this little symbol that you see here, the O with the baseball cap, that is the Greek letter sigma. But you're not going to call it sigma. You're going to call it the Stefan Boltzmann constant.
I have a really quick question.
Yeah.
If we call it sigma, like on our like work, would it be marked wrong or
It would piss
not?
you off. You
Okay, so don't do it.
Yeah, like use the. Can you draw a little O with a hat? Oh, are you one
Yeah.
of those? Are you one of those mad typists? Are you one of those mad typists?
No.
Okay, because I was grading some papers this week, and literally someone was trying to write out their math. I kid you not. P squared is equal to A cubed, and I almost threw my laptop.
Oh no,
out
that's
the
too
window.
much work.
I was like, don't. And I told that person, you're not allowed to type anymore. You're grounded. You buy a pencil and some paper, and you're gonna write it just like everyone else. Because I'm not looking at this bullshit.
You imagine that he submits work and it's written p squared equals a cubed.
But people don't have a lot of background in science and math. They don't know what is okay and what is not okay. Anyways, the reason why I mentioned it was sigma is when an astronomer talks to another astronomer, they'll say brightness is sigma t to the fourth. They'll sometimes just say sigma t to the fourth. But you shouldn't need to call it sigma. You should just make the little symbol. And what's more important is it has a value of 6 times 10 to the negative 8. I hope you can read that. And the units are watts per meter squared per Kelvin to the fourth power. Like I said, I kind of screwed this class up. I should have introduced this real slow and gentle and then given you some sample problems to make you feel good. I totally don't have time for that today. I have to make you feel bad. So just write it down, okay? Now, the second effect having to do with black bodies is that more temperature equals, how should I put this? Bluer light. Light that gets bluer and bluer and bluer. And that's described by a formula called Veen's law. And that's a very simple formula. It tells you that the peak wavelength, the maximum wavelength emitted by your light source, is 3 million divided by the temperature. And we're going to put some units here to make the units work out. It's 3 million nanometer kelvins. This makes sure that if I plug my temperature in kelvins, my wavelength will come out in nanometers, which is good for visible light. Okay, you're not going to understand these formulas until you try them, but I totally busted my budget. I screwed this class up big time today. Let's take a 15-minute tea break, and then we're going to be using these formulas in our homework today. Our homework today is not too long and hard, but we needed those formulas to be able to do it. So I didn't feel good about going forward until we got them down. But this is very interesting stuff. So I'm psyched that you guys are having questions about it. I find studying light really, really interesting. It's something that appeals to me. All right, take a little break. Cell phone time, I'm at 1:45. So at 2, we'll start the homework and we'll be done by 3, okay?
Sounds good.
See you in a bit. Okay, folks, let's try to get into it here. We got homework to do.
Professor, I have a super quick question before we start.
Sure thing.
So, you were telling, like, you showed us that picture of that really heated piece of metal, like in that blacksmith shop.
Yep.
And you said if you put that prism up to it, you can see a rainbow.
Yep.
So would that still apply to like a taken image? Like for an example, like that, if you would have put up that prism to that image on Google, would you still see the rainbow or would it get messed up because it's on a screen?
Right. So it wouldn't look the same on the screen because the screen is generating it by a different mechanism.
Yeah.
While the screen is a faithful reproduction of what it would look like to your eyes, the light that's being generated in the image is being generated in the computer screen itself from those pixels, right? So what you would see was a spectrum from the pixels itself. For instance, what's happening when we look at that digital image is, let me just show you, it actually uses something closer to the law of emission to do that. Every single white pixel, let's go to like a picture of a glowing metal, right? So for instance, here's a picture of what would be a black body. If we were reality standing in front of that light bulb and we held a prism up, we would see the rainbow. But here, that orange band that you see is being made up of individual pixels, and there's something called the Bayer matrix. Each white pixel that you see is actually a combination of 3 micropixels. One pixel, which I could draw here, is actually 1 red pixel, 1 blue pixel, and 2 green pixels. You'll remember that the human eye is more sensitive to green, so that they oversample green when they reproduce the image.
Oh, when I was a kid, I used to sit really close in front of the TV, and sometimes I would see like those patterns like along this.
Right.
Makes
What
sense why I
happens is
saw
if
it
you,
now.
it's like if you're eating cereal or you're drinking some water while reading your iPad or your iPhone, sometimes a drop of water will actually fall on your iPhone or your iPad screen, and that little drop of water becomes a little magnifying glass, and you actually can see the Bayer matrix underneath it.
Yeah.
So here's my point. Each of these squares are generating light through the process of emission. These are not black body lights, but they're little quantum circuits that are generating a pure blue light. And they're mixing it together to create the illusion of white light. In fact, I'll tell you what we could do. I can tell you, I don't know if I can show it to you, but if I were to just leave this white screen up and I take out my spectroscope, okay, I see something that looks like a rainbow, but it's not really a pure rainbow. There's a little band of green, a kind of band, or a big band of green, a big band of red, and a small band of bluish purple. So it's technically an emission spectrum that's coming from this screen, even though they're trying to fake reproduce what looks like a black body. The real black body, you'd have to be in person to see it. Does that answer your question?
Yes, it does answer
Okay.
my question.
Remember,
Thank you.
it's the screen that's generating the light, so it's not fair. It's not actually a glowing piece of metal. It's electrons that are creating that light. Okay. Today's homework is homework number 5. There's a couple problems from chapter 5, a couple problems from chapter 6. It's all related to the stuff that we've been talking about. Put your name on the paper. Put AS1020 in your section. This is homework number 5. It'd be great if someone could read me the problem numbers. It'd be great if you guys could open up those questions so I can ask you to take turns reading. Let me get my tea while you look that up.
I have the numbers.
Only one kind of snack makes sense when you're studying astronomy. Okay, what's the chapter 5 problems?
55, 58, and 60.
And the chapter 6 problems?
51 and 54.
Okay. We kind of didn't quite get to the chapter 6 material, but we're just gonna wing it, okay? So let's start with chapter 5, number 55. This should be an easy one. Mateus, it sounds like you've got the questions ready to go, so we'll just ask you to start us off.
Okay. All right, so number 55. Oh, it's not on part 1. Let me go back to the part.
What, I'm sorry?
Okay, so number 55, UV photon. What is the energy in joules of an ultraviolet photon with wavelength 120 nanometers? What is its frequency?
So they've asked us for 2 things. They asked us for the energy, then they asked us for the frequency, and they gave us a wavelength of 120 nanometers. This is very similar to the kind of thing I'd ask you to do on a test. Let's see if you guys can hack it. It might be a good idea for me to send you guys the formula sheet. I wonder if I could do that. I want to send it to everyone. I'm going to email the entire class the AS1020 formula sheet. This could be helpful as we're going through our lecture today. Oh, everything's still messed up. I want to do this before I forget. And I don't want to just send it to the group here. I want to make sure that all students later on can get it too. AS1020 formula sheet. And I'm just going to attach this and move on. Choose file. Okay, geez, that took a while. If you guys check your email, you should see a formula sheet pop up that you can use. You can use it for this homework and start practicing right away. Okay, I'm lost. What do I do?
Just give me one more second.
By the way, at the beginning of class, I mentioned the Mars Perseverance rover that's landing today. I believe it's happening around 4 p.m., so shortly after our class ends. And I think this time they've attached cameras to the landing module so that you'll actually be able to see a video at some point of the spacecraft's descent to Mars, which hopefully will go smoothly. And once again, if you just go to that, I just want to say this again because it's kind of extraordinary. If you go to that NASA Perseverance webpage, they've got all kinds of cool infographics on what's going to happen here. One of the cool things is not only does this have a bunch of cool instruments and cameras, but this spacecraft actually contains a little drone helicopter, and it's going to launch the first ever unmanned flight on the atmosphere of Mars. And this drone helicopter is going to come off the thing and fly around Mars and survey the area. So I'm just kind of showing you that they have all these cool animations. They show you like the demo of the helicopter in action. It'll be really cool to watch this thing land because, like I said, I don't know if there's a picture of it here, but it's going to have this little, there's going to be this little rocket ship that kind of flies around Mars. There's a picture of it there, and it's going to be holding the craft, and then it's going to lower and descend it by a kind of crane. The whole thing is just going to be wild. I don't have time to get into the whole thing, but it's something cool that's happening today in space exploration. Okay, we've got an ultraviolet photon, wavelength 120 nanometers, got to find its energy and frequency. I want you guys to work with me. What should I do?
All right, so first you need to convert the wavelength into MKS units.
Very good, very good. So let's do that first. So let's convert wavelength to meters. And how would I do that? Obviously with dimensional analysis, right? Oh, you know who our resident expert in dimensional analysis is? Mateus. Mateus is going to help us out with that. Mateus, let's go through the steps together.
All right, so 150 nanometers.
Sorry, 120, right?
120, sorry.
That's all right. All right, so we write that down, and then what?
Times division bar.
Good.
Nanometers in the bottom and meters on top.
Okay. That cancels out our nanometers.
Yes. 1 nanometer is the equivalent of 1 times 10 to the -9.
Excellent. It's a billionth of a meter. That's what nano means. Okay, do you want to just glue those together? Like Mateus, yes, you could punch this into your calculator, but it's way classier if you just multiply 120 times 1. So what's my answer?
120 times 10 to the -9.
Yeah. I like to write it this way because in my mind, Mateus, this says 120 nanometers, where instead of writing the word nano, we've now made it a billionth. Okay, now what are we going to do? It's time to find the energy and the frequency. We need some formulas. What formulas do you want to use?
Can we switch up the first one?
Speed of light is wavelength times frequency.
Yeah, and then you pass the wavelength to the other side, dividing it, and then it would be frequency equals c over wavelength.
Excellent. And we know from our formula sheet that you now have, the speed of light is 3 times 10 to the 8 meters per second. Sorry, I'm not color coding my units right now. And 120 billionths of a meter. Why don't you guys punch that up for me?
Oops. 2.5 times 10 to the 16th.
And what are our units?
Let me look at the numbers. Seconds?
Not seconds.
Cycles per second.
Yeah, because seconds is technically in the bottom.
Mm-hmm.
So it's cycles per second, which is the same thing as hertz. So you could either write it as 1 over seconds or hertz, or you could even write it cycles per second. So there's our frequency. Now let's get our energy. This shouldn't be too hard.
So I used energy equals Planck's constant times c over lambda
Okay.
to work with the givens. So since you have everything, you just basically plug it in. I used 6.63 times 10 to the negative 34th joules second.
Okay, so so usually when I give you guys Planck's constant, I just make it 7 times 10 to the negative 34. But since Vladimir used a couple of extra digits, let's just go along with that for fun. We'll do 6.63 times 10 to the negative 34. Here I will use colors for the units. Joules times seconds. Vladimir, probably just getting in the habit of using 7 is better because it's just faster and easier.
All right.
3 times 10 to the 8 meters per second.
And then divided by 120 times 10 to the negative 9th meters.
Good. And did you punch that up?
Yeah, that comes out as about 1.66 times 10 to the negative 18th joules.
Let's just keep 2 sig figs. 1.7
Right.
times 10 to the negative 18 joules.
Oh yeah, 1.2 sig figs. Never mind.
Wait, I'm sorry. What the freaking answer?
What?
Is this correct?
I don't know. That's what I got.
I don't know. That's what I got. Did anyone else get this? Did anyone else do it? Is anyone alive out there?
I'm doing it right now. I was still copying down.
I got that.
Okay. That's
Well,
reassuring.
yeah, no, I got that. I think, no, I got to the 16th, but
What do you mean to the 16th? That matters. This is the most important part of the number.
Well, I also noticed this. I would try doing the one before too, where we got the answer 2.5 times 10 to the 15th, because I think that was also different.
Shit. Oh, hey, sorry. I meant to silence. Can I call you back? I'm doing an office hours right now. Okay, bye-bye. Sorry, that's the old man. So you're saying not everyone got this? Let me punch it. 3 exp8 divided by 120 exp negative 9. 2.5 to the 15th. Oh, how'd you get? Are you using a weird calculator? Who did this?
Shouldn't it be to the 15th?
Yeah, that's what I got. Okay, that's why we all have to punch so that we don't make these mistakes, guys. We can't just rely on any one person, including me. But this should not change, right?
No, I'm pretty sure it's correct.
Yeah. Okay, so we're done with that problem then. That was easy.
Okay, because this is what I got. I don't know if you can see that.
There's no way, because look, add your powers, and Mariah, you'll see you can't be right. Negative 34 plus 8 gives you minus 26. Minus 26 plus 9 is going to give you negative 18-ish, you know, like it. There's no way. Well, not exactly, actually. Negative 20, but then you lose 2. Look, there's no way you can get positive power. Do you agree with me? 34 is greater than 8.
Yeah, it makes sense.
So you probably forgot to put your negative in there is what I think you did. Or something. Did you confirm that, Mariah? I want to make sure we all feel good.
I'm trying to punch it in, but honestly, my dogs are distracting me. So give me a second.
Let's ask Pippa what Pippa got. Pippa, did you punch it in?
No, I just got back, so I'm trying to catch up on all the notes.
All right, get all that down because we've only done one problem.
Sometimes it feels so weird to be in a live lecture because I usually so I used to watch your lectures at 1.75 or 2 times the speed, and usually you're just zooming through everything, talking very fast, and you're like, when I slow down, it's like feels
Look,
like you're saying like,
guys, you know what this feels like for me? This feels like trying to swim through molasses. I can go so much fucking faster than this if you guys can keep up with me, but I can only go as fast as you guys can think and punch. So, Taryn, did you have enough time to get all this? I don't want to leave you behind, Taryn.
So I've done it like 3 times now, and I'm still getting negative 18th for the exponent. Oh,
Okay.
wait, that's what you have.
Yeah.
Okay, never mind. Yep, that's all right.
Taryn, where you at, buddy? Talk to me.
I'm good.
You got all that?
Yep.
Awesome. Let's just move on. This has just been a weird day from start to finish. This day is weird. Okay. It's not your fault either. I've been very unsmooth. I've just done some stupid things. All right. Let's go on to 58. Who's got that stuff in front of them? Who can read me?
I can read it.
Thank you.
So
58.
So it's the thermal radiation law. Loss, actually, S with the S.
Thermal radiation basically means black body. That's what they're saying. We're going to study black body light. Okay, what's it say?
A. Find the emitted power per square meter and wavelength peak intensity for a 3000 Kelvin object that emits thermal radiation.
Okay, let me explain what they're asking for. They're being really weird. Sometimes the book just does weird things that I don't like. They ask us to find the power per square meter, which is a really goofy ass way of saying, please find the number of watts per meter, which really means they want us to find the brightness.
Yeah, so we're gonna have to use the Stefan Boltzmann law and Wayne's law, or
That's
Wien's
right.
law.
So for this, we're going to use the Stefan Boltzmann law. They also want us to find, they called it the wavelength of peak intensity, and I call it lambda max, the wavelength at maximum of your black body. So black bodies, for instance, they always emit all the different colors of light. Like a white light bulb will emit all the colors of light, but one color is always emitted more than any other. Lambda max is the wavelength of peak intensity. So I'm just helping you translate from book speak into mathematics speak. So we have two jobs to do. They've given us the temperature of 3000 Kelvin. 3000 Kelvin is close to the temperature of this light bulb filament. So this is comparable to the temperature of a simple 40-watt light bulb. It's also comparable to the surface of the star Betelgeuse. Let's first find the brightness using the Stefan Boltzmann law. Brightness is sigma t to the fourth, where sigma is the Stefan Boltzmann constant. The Stefan Boltzmann constant is roughly 6 times 10 to the minus 8 with units of watts per square meter per Kelvin to the fourth. That number is always the same. Don't worry about it. It's got some secret physics packed into it. Times the temperature, 3000 Kelvin. And we're going to have to raise that to the fourth power, which I don't think you guys have done before. All right. Let me walk you through this puppy first time around. First, let you finish copying. I'll sip some tea.
Is it 18 times 10 to the fourth watts per square meter?
No. I don't
No.
think. Let's try it together, all right? First of all, I'm going to have to focus.
Ah, never mind. Okay. 81 times 6. All right.
Hold on. Let's just do this slow for everyone. Now look, everyone, do you guys see this button here? X to the power of y? That's your raise to the arbitrary key. So for instance, if I were to take 2 and raise it to the power of 4, I would get 16, which is 2 times 2 times 2 times 2, right? Okay. So let's try it out here. Is everyone with me? I only see 4 humans here. Where's my other humans? Where are my humans at? Okay. Taryn, Kiana, I want to see you. I want to know that you're with me. Okay, here we go. 6 exp negative 8 times, I'm going to do 3000 to the power of 4 equals. Okay, so Taryn, do you want to put that in a scientific notation for me? Is that what you got in your calculator? Mateus got it. Taryn, I can't hear you. I don't know if you're talking to me or someone else, but.
486 times 10 to the fourth.
That's not necessarily good style.
Okay.
This is a number of order million, so I think you should just put it into proper form.
Okay.
I mean, first of all, did you get it on your calculator?
I did.
Okay. So how would you put that into proper scientific notation?
I can't see. Okay. I would put 4 point. Yeah.
Want to just round it to 4.9?
Yes. Times 10 to the fifth.
Count better. There's your decimal point, right?
Oh yeah. Is it 7?
One, no, look. 1, 2, 3, 4, 5, 6.
Oh, okay.
Right?
Yes.
You got a whole menagerie back there. I can hear the birds. All right. What are my units?
Meters.
Nope.
What?
Watts.
Is it what? The watts? The watts?
Well, look, watts are definitely left behind, but look, this Kelvin is going to be raised to the 4th power.
Okay.
So you're canceling out Kelvin to the 4th with Kelvin to the 4th. So what's left?
The meter square.
Well, hold on. First of all, the meters squared are on the bottom, but there's also watts. You got to give me the whole thing. You guys are giving me little pieces of the answer.
Okay.
Does anyone understand?
Watts divided by m to the second.
Yeah. So Taryn, sometimes you were saying watts, sometimes you were saying square meters.
Yeah, like I wasn't sure which unit to start with, but
You
I guess
start with whatever's in the top.
right.
So watts are on the top per square meter.
Is it just me, or I guess like the when someone talks, I hear
It's
their
called echo, and I think here. Well, I just stopped. It was Philemon. Philemon was giving us the echo treatment. Sorry, buddy. So I had to mute Philemon for a second just so I could avoid the echo city. All right. We have to get the wavelength of peak intensity. Now, I'll box that. Now we're going to use Wien's law. For the second part, we have lambda max is 3 million nanometer kelvins divided by 3,000 Kelvin. You guys should probably be able to do that in your head, but
1 times 10 to the 3 nanometers.
you don't need to put it in the scientific notation.
Oh, okay.
How about I give you a
1,000
2.5 times 10 to the 1 today, huh? What is it, Vladimir?
1,000 nanometers.
Okay, let's see if you're a tough guy. How many microns is that?
Oh, that would be 1 micron.
Okay, let's see if you're still a tough guy. In what regime of the electromagnetic spectrum is
I believe that would be radio waves.
Nope.
No. Infrared, of course.
Yeah, 700 nanometers is red, so just past that would be infrared. Have you ever put your hand up to an incandescent light bulb and felt the heat coming off of it? Your hand is detecting the infrared radiation. It's like a little baby toaster that's heating up your hand.
I just have a quick question.
Yeah.
It says the box thing, it says 1,000 nanometers equals 1. How do you say the end part of that?
So this is the Greek letter mu. Mu. It's like something between an M and a U.
Okay.
But astronomers often use the symbol mu for micro. In the metric system, micro means 1 millionth. So we would say that 1 micrometer, or sometimes people say 1 micron.
Okay, thank you.
One of the astronomers that I worked with, astronomers tend to work in different bands of the EM spectrum. As an undergraduate, I worked in the University of Arizona infrared lab, working on infrared detectors. This guy, George Reiki, he was the boss of the wing that I worked under. And he wrote some famous, real techie astro book, Detection of Light from the Ultraviolet to the Submillimeter. The point being, which is, I only work in the infrared and anything else is boring. I mean, he did have a little bit of visual light stuff in it too, but like for this astronomer, like he wouldn't even look outside of the infrared at a star. One of my astronomy professors was literally a radio astronomer. he was a radio astronomer, and one day he said to me, he said, optical astronomy sucks. You can't see anything with it. In other words, he wouldn't have even dared, he wouldn't have even bothered to look through a telescope like this because it operates at the visible wavelengths. Like it's just what's boring to him. If you were like, hey, you want to look through my telescope at this cool nebula? He'd be like, nah, I'm all set. All right, let's do part B. It's just the same thing, okay? I'm gonna erase this. Okay, what's part B say, Vladimir? They give us-
So it's all the same thing, but the temperature is 50,000 kelvins.
All right, so first we'll calculate the brightness. It's sigma t to the fourth. So 6 times 10 to the minus 8 watts per square meter per Kelvin to the fourth times 50,000 kelvins to the fourth power. Punch them up.
So that comes out as 375 billion, well, times 10 to the 9th watts per meter squared.
So
times 10 to the 9th.
let's do 3.8 times 10 to the 11. The way you said it was totally okay. Actually, you know what? No, I want to go with Vladimir's method.
I actually put 11 first, and I was like, well.
No, you were right. The more I think about it, so you said 375 billion, right?
Yeah.
Times 10 to the 9. And what are my units?
Watts per square meter.
I actually like your method better now that I think about it. 375 billion watts per square meter. How about the wavelength of peak intensity? That's 3 million. Nanometer kelvins over 50,000 Kelvin.
$600 nanometers.
You're off by a power of 10 somewhere.
Try to do it without a calculator.
Well, because look, 6 minus 4 is 2.
2, yeah.
But 3/5 is what the hell is
0.6. So it's 6.
So you have to take 60, right?
So it's 60 nanometers. Wow, it's pretty hard.
Hey, in what regime of the electromagnetic spectrum?
I'd say ultraviolet.
Very good. You are good. UV. How did he know that, class? Because he knows 400 is the cutoff for violet, and this is short of 400. So it must be ultraviolet.
And then the cutoff for ultraviolet is 10 nanometers.
That's right. Very good. That's the kind of thing I want for us to have an intelligent discussion. That's nice. Okay. 2 down, 3 to go. Who haven't I talked to in a while? Kiana, you feel like reading one?
Yeah, let me just pull it up.
We're looking for chapter 5, number 60. I'm going to erase.
Okay, I found it. All right, so it says, taking the sun's temperature, the sun radiates a total power of about 4 times 10 to the 26th watts into space. The sun's radius is about 7 times 10 to the 8th meters. And then A says, calculate the average power radiated by each square face area of a sphere. A equals 4 pi R2.
Let me give you another way to interpret this. They want us to find the brightness at the surface of the sun. Let's draw the picture. Here's the sun. It has a radius r. We're going to imagine dividing the entire surface up into a bunch of square meter panels. By the way, a square meter panel is roughly the size of this dry erase board that I'm using. You guys will notice that it's about 1 meter tall and about 1 meter wide. So we're basically saying if I laid this flat panel down on the sun, how much light would be coming through it? Do you guys remember what formula we want to use for that?
Yeah. It's brightness equals luminosity of an object divided by its surface area. So 4 pi r squared.
Yeah, the surface area of a sphere is 4 pi r squared. That's something you learn in your geometry class. Okay, so we have everything in MKS units, which is wicked convenient. So the brightness will just be 4 times 10 to the 26 watts over 4 over pi over 7 times 10 to the 8 meters squared. I want everyone to try this because there's a few tricks in here. I'm guessing about half of you are going to get this wrong when you punch it into your calculator. And we're going to want to have a talk about that.
So we're keeping just 1 sig fig.
Sure. Yeah, 1's fine. You can do 2. 1 is okay. I don't care. Actually, let's do 2.
Yeah, I'll do 2. So I gave it a shot. Let's see if it's correct. I got about 65 times 10 to the 6th watts per meter squared.
Nice. So Vladimir, the nice thing about working with you is we can go fast because you tend to get it right the first time. But let's slow down and check up on everyone else here to make sure no child is left behind. Oh, okay, Mariah's got it. Who else has got it? Mateus has got it. So Vladimir, Mariah, Mateus are good. How about Andrew, Kiana, Taryn?
I don't know what the hell I did, but I didn't get anything close to that.
All right, show me what you got. Hold your calculator up.
The division at the bottom.
So I know what you did wrong, Kiana. Yeah, you have to divide, Andrew. That's the point. Taryn, how did it work out for you? Buddy, old pal. Sorry, you're muted, buddy.
I was still trying to type it out, but I can't see.
Oh.
I was still taking it down.
Can you punch it quick like a bunny? Don't forget that square there. Okay, Andrew looks, hold on, Andrew, keep that right there. Keep it right there. You're a little off, Andrews. So you did something weird. Kiana, I want to talk to you about what you did. When you get to this part, Kiana, you've got to actually hit divide. Divide by 4, divide by 10.
Oh, yeah.
Want to try it again?
I multiplied. Yeah, I'll try it again.
Try it again. And Taryn, I want to see what you got. And Andrew, I want you to fix your mistake.
Okay, honestly, I think I still got it wrong, but I did get a different number this time
The
though.
room is so dark, I can't even believe your calculator works.
Yeah, I don't know why. Like
Taryn,
it's
hold it up. Taryn, hold it up. What do you got? Taryn, you've been punching at that thing for like 2 hours. I'm gonna grow old and die here.
I know I kept hitting like the wrong button.
All right, well,
Um,
look. Here, all right, look, fuck this. Well, all right, you guys are fired. Just punch after me, okay? You gonna
I'm
do it?
sorry.
No, it's all right. Just here. Come on.
I was like at pi. Like that's what I have so far. I needed the last.
All right, well, just do
Division.
it. I don't. For me, it's so fast. Like,
I can't see the number.
well,
Okay. Okay.
Oh, wait, did I get it this time around? I don't think I did.
it looks. Hold on, Andy. Hold that up. No. All right, we have to do this.
Okay.
All right, everyone, just punch after
You want a
me.
berry?
Ready?
Yes.
4E26.
I need a berry.
Wait, hold on.
What you got, Taryn? Taryn, show me.
Is that?
Oh wait.
Hmm?
Oh, Phil, I want to see you too.
Apple.
Taryn, no. Yes, Philemon, you got it.
Oh,
Okay.
is it
look.
divide the pie? Do I have to divide the pie?
Yes. Here,
Oh,
everyone.
all right. I think
Everyone
that's
just watch me. Everyone clear it out. Hit clear. Taryn, Kiana, and Andrew. Follow me. 4E26. Divide by
Sorry,
4.
It came off the stick.
Oh my gosh.
Are you in class?
Yeah.
Oh, I'm
But
so sorry.
No. I can't. They can't hear you.
Yes, we can. We can hear it loud and clear.
Oh.
Divide by pi. Divide by 7E8 squared equals. Look, that should take 10 seconds to do. Let's watch that again. 4E26 divide by 4 divide by pi divide by 7E8 squared equals 10 seconds. Hold up the calculator and show me that you got it. If you haven't proved it to me already, like Taryn, Kiana, Andrew. Taryn, you got birds and parakeets and moms and dads. All right, Andrew, looks like you got it now. So you're eating Easter eggs. Come on, show me what you got here. Kiana, did you get it?
Yeah, I started typing the whole thing and then I was like so into typing it that I didn't realize the stupid solar wasn't even hitting it, so I had to retype it in. But I'm almost done
Wait,
though.
so was that a yes or a no?
So it was a no, so I'm retyping it.
Could you do it quickly? All
Yeah,
right,
I'm almost done. I just gotta punch one more thing. Oh god.
let's move on to the next. Taryn, did you ever get it?
No, it kept giving me this really weird number, so I don't really understand what I'm doing wrong.
All right, so do you want to follow me again this time? No distractions?
Yeah.
I want you to keep your microphone on and I want you to say okay every time you're ready to proceed, okay?
Okay. Yes.
So have you cleared out your calculator?
I've cleared it out.
4E26.
Okay.
Divide by.
Divide by.
Huh?
4.
I'm sorry.
Okay.
Divide by.
1 to the 26.
So, all right, okay. We need focus here. Taryn, we'll restart again.
What?
I can't move on until I know you've punched what I've punched into your calculator.
I had the same thing. It said 1 to the 26.
Okay, yeah, but here's how this works. You say okay, and then I give you the next step. All right,
Yes.
so I'm distracted now because I'm very confused. So let's clear it out. Let's do it again. Every time you say okay, I'll give you another key.
Okay.
4E26.
Okay.
Divide by.
Yep. Okay.
4.
Okay.
Divide by.
Okay.
Pi. hit this key.
Okay. I did.
Divide by 7 exp8 square
Okay.
equals. Kiana, how about you? You with me here?
Okay. Which
I got it now.
one is the square key? Because I'm confused right now. That's all I need to hit and I'm done. Okay.
Well, you hit square and then you hit equals.
Yeah. Okay. Yes,
Did
I
you
got
get it?
the same thing this time.
Jesus.
I don't know what I'm doing. I think I'm just like dividing at like the wrong spot. And I think that's what's throwing the whole thing off is like the confusion with like the multiplication and the division. Because other than
My
that, I
concern
got
is
it.
I want to work these kinks out now. I don't want you to be having them during the test. I want these kinks getting
Yeah.
worked out right now. We only got one more week till the test, so no more kinks. Okay, go on, Kiana, and read us part B.
Okay.
Everybody's got that, right?
Yes. Okay. Part B says, using your answer from Part A in the Stefan Boltzmann Law, calculate the average surface temperature of the sun. Do you want me to read the little note that's there or?
Yeah, why not?
Okay. Okay. Note, the temperature calculated this way is called the sun's effective temperature.
Right. In other words, you can't measure the temperature of the sun by sticking a thermometer into its photosphere, right? You can't, well, we are flying to the sun, but we don't have an ability to put a thermometer into the surface of the star. We do calculate the brightness of the star, and then we reverse engineer this formula. First, we'll divide both sides by the Stefan Boltzmann constant. And now we have brightness divided by sigma is t to the power of 4. Do you guys know how we get rid of a fourth power? How do you kill a fourth power?
Take the fourth root.
That's right. So the effective temperature is the fourth root of brightness over sigma. You might want to take a box around that because you're going to be using that in the future. This is known as the effective temperature. We have the brightness from part A, and this is a constant of nature. So we can plug in to get the brightness is the fourth power of 65 million watts per square meter divided by 6 times 10 to the negative 8 watts per meter squared per Kelvin to the fourth. Okay, this time we're going to do the whole thing together because I might as well just punch it in and have everyone should just follow me.
I gotta copy the rest. I can't see it.
And I should have made my fourth root a little bit neater there. Should be go all the way down. Andy, let me know when you're done.
Did I tell you the answer?
No.
Okay.
No, I'm done letting you guys punch it in. You're just follow along, okay?
Right. Okay. Got it.
Taryn, Kiana, you're with me, right? All right. 65 exp6 divided by 6 exp negative 8. Now equals, okay, here's the deal. We're about to take the fourth root. Let me get my autofocus up here. The fourth root is the same thing as raising our answer to the power of 1 over 4. So this key here, x to the power of 1 over y, that's kind of like your arbitrary root key. So what we're going to do is we're going to hit shift, then we're going to hit x to the 1 over y, and then we're going to hit 4, and then equals. You should see this number on your screen.
What is it? Shift. And then
X to the 1 over Y. And then 4. And then equals. Did y'all get this?
is it equals?
Yes. Okay. All right. I like what I'm seeing. I'm seeing a whole bunch of good answers. And Vladimir, is that what you got the first time around?
Yeah, I rounded it to 5,700 kelvins.
I love it. And notice Vladimir's got good control over his units there, right? He can see that watts per meter squared cancels with watts per meter squared. And 1 over kelvins to the fourth are kelvins to the fourth. And the fourth root of kelvins to the fourth gives us 5,700 Kelvin. And that's approximately the surface temperature of the sun.
Do we need to change the units when we get Kelvin as the final answer in this case?
What do you mean by change the units? I don't understand that term.
The temperature unit from Kelvin to Celsius or Fahrenheit.
No.
Oh, not really, because it's the space and stuff. It's space and stuff.
In science, people prefer Kelvin. And secondly, Mateus, if you were to translate that into Fahrenheit, it'll just be some shitloads of thousands of degrees Fahrenheit. As you start getting up into the thousands of degrees, it's all kind of the same. Like, just out of curiosity, because I don't feel like doing the 9/5 plus 32 plus 273. If I were to do 5,700 Kelvin to Fahrenheit, okay, so it's 9,800 Fahrenheit. I'm not saying that's exactly the same. I'm just saying, what's the difference? It's all at a crazy hot temperature. All right, we're going to move on to chapter 6. These next two problems are pretty simple in calculation, maybe a little trickier in understanding. Mariah, can you read us chapter 651? Hold on, Andrew.
Yes, I
erase all
can.
this?
Yeah, you can erase it. I'm all set.
All right.
Can I ask a quick question before we move on to the next problem? Why are there two symbols for sigma?
There's usually an uppercase and a lowercase. This is lowercase sigma.
Doesn't the other one look like a backwards E?
Yeah. This is a book. Look how dog-eared it is. I had to take this. This is my little cheat sheet all throughout college. And whenever I started to flounder on Greek variable stuff, they had a nice little page here showing you the upper and lower case. I mean, unless you're like a frat boy or something, you really, or a mathematician, you don't know this stuff. Or I guess if you study the classics. So let's look for sigma. Where's sigma? Oh, there's sigma. So the uppercase sigma, yeah, it looks like a kind of a capital E that's a little bit angular.
Yeah.
So in mathematics, they use capital sigma for summation if you add a bunch of numbers together. But in physics, the lowercase sigma usually represents the Stefan Boltzmann constant. Just a thing.
Oh, okay.
So it's just like uppercase Q looks a little bit different than lowercase q.
Why did
Yeah, I only asked because I saw the other one first, and then you introduced this one, so I was like, oh, there's two different sigmas. I was confused.
Yeah,
why do frat boys know the Greek alphabet? Oh, I'm sorry for interrupting.
No, what were you asking?
I said, why do the frat boys know the Greek alphabet?
I don't know, because they're all because they use Greek letters for their fraternities, like I Delta Epsilon or something, whatever. That was a dumb joke. It was just don't even pay any attention to me, okay? I'm just making dumb jokes. Okay, let's do chapter 6, number 51.
Okay. Closed binary system. Suppose that two stars in the binary star system are separated by a distance of 100 million kilometers and are located at a distance of 100 light years from Earth. What is the angular separation of the two stars? Give your answer in both degrees and I forgot to say this word. It's like
arc seconds.
Arc seconds.
Okay,
yes.
What I want everyone to do in this picture is I want everyone to draw a little diagram with me. On the right side of the page, I want you to put two binary stars. And these two binary stars are separated by what Mariah said was 100 million, was it kilometers? Or was it 100 million? Yeah, 100 million kilometers, right?
Yeah.
All right. Now we are over here on Earth. This is the observer on planet Earth. And we're looking at them from 100 light years away. And they're going to make some angle on our sky. And we know that they're 100 light years from Earth, from us.
Wait, don't tell me the small angle formula comes back to life.
Yep. Oh, the small angle formula. Basically, what I've been doing in the
yes.
first part of this class is I've been building up this toolkit, and we're going to start using them. Now, in the original small angle formula, I used to call the angle theta. But theta was good when we were using degrees. Like I used to use this version of the formula. The angular size is 360 degrees over 2 pi times the separation divided by the distance. This is the chapter 2 version, and it's not really going to be helpful for us. And the reason why we don't want to use this one is this one was good to get your angle in degrees.
Do you need radians now?
No, radians are even more clumsy. The units
really?
that astronomers like are arc seconds. Because usually the stars are so close together that the angle between them is very, very tiny. As an example, this might not be the best angle. Well, these are maybe a few arc seconds apart. I love to take people out to the telescope and show them this binary star called Albireo. Albireo is in the constellation of Cygnus the Swan. And it makes for just like a pretty spectacular sight in a telescope because the two stars have dramatic colors. They're so close together that to your naked eye, they actually blend into a single star. If you were to look at this in the sky, it would just look like a single star. But once you look into your telescope field of view, the telescope separates and reveals them into a beautiful binary pair. In reality, these stars could actually be quite far apart, maybe 100 million kilometers or so. But you're seeing them from so far away that the angle that separates them is too small to measure in degrees. Instead of using theta for angle, in chapter 6, we're going to switch over and we're going to use alpha for angle. And the reason I chose alpha is it kind of looks like an A, and then it reminds you that we're going to want to have the answer in arc seconds. So the new version of the formula, the angular separation is 206.265 arc seconds times S over D. And here, S is the separation between the stars, and D is the distance from you to the stars. Alpha is going to come out for us in arc seconds. They said they want the answer in degrees and arc seconds. I'm going to change that. I don't even want the answer in degrees. It's pointless. Let's just get the answer in arc seconds. However, I'd like to point out that S and D are both distances. That's a distance and that's a distance. And in this formula, we need them to be in the same units. So guys, we either have to convert 100 million kilometers to light years or 100 light years to kilometers. What do you think is easier?
Probably light years into kilometers.
Yeah. So let's start with 100 light years. Let's make a division bar. What units do I want? Oh my God, it's 311. God, this day just got so screwed up on me.
Light years on the bottom and kilometers on top.
I don't remember. Is it 10 times 10 to the negative 10 to the 19th kilometers?
No, it's 9.5 trillion per light year. So one
okay.
year is 9.5 trillion kilometers. You'll notice that that's on your formula sheet that I just emailed the class. Can anyone do that in their head? That shouldn't be too hard.
9.5 times 10 to the 14th kilometers.
Good. He just added 2 zeros. Okay, now we're going to plug them into this version of the small angle formula. The angular separation is 206.265 arc seconds times 100 million kilometers over 9.5 times 10 to the 14 kilometers. Punch them up quick.
Over to the landing team, and it looks like team leaders in mission control are about to talk to both teams. So let's listen in.
The CDM change, as I mentioned previously, is due
Is it 1 or 2
It's like the landing
6?
team's taking over for Perseverance. That's a thing. What's up?
1 or 2 sig fix. I think 1, because we have the crappiest number is 100, right?
While technically you are correct, Vladimir, let's cheat. When in
Alright.
doubt, choose 2. I'm still waiting. Was anyone going to give me the answer, or
I can.
just give it to me?
All right. So it's 22 1,000ths arc seconds.
No, could you just give me a decimal version, please?
Okay, 0.022 arc seconds.
I changed my mind.
Any way I can see what that looks like on the calculator?
Yeah, I changed my mind, Vladimir. I only want 1 sig fig. See what a bastard I am? The simpler way to say that is 2/100ths of an arc second. Or I guess, yeah, 22 thousandths. All right, ready? You watching, Kiana? 206.265 times 100 exp6 divided by 9.5 exp14.
Okay, I got that.
Yes. Was there any other part to that problem?
Let me check.
I think there was one extra little part.
Yeah, like they're
Says, can the Hubble Space Telescope resolve the 2 stars?
Okay. So in the book, which nobody reads, it tells us the following information. It says the Hubble Space Telescope, the best optical telescope in the world, until they launch James Webb next year, has a minimum angle of resolution of 0.05 arc seconds. Can Hubble resolve the 2 stars?
No.
No. Hubble cannot.
So will James Webb be able to resolve the 2 stars?
Yeah. James Webb is 3 times the diameter. The next question will explore that. No, Hubble cannot resolve the stars because 0.02 arc seconds is less than. Here's a question just to see if you guys understand. Suppose Hubble were to look at the 2 stars and take a picture. Can you guys tell me what it would look like in the field of view? What would Hubble see if it tried taking a picture of those 2 stars?
Would it look like that conjoined star? I mean,
Yeah.
not literally conjoined, but like they'd like overlap and look like one.
It would just look like one star. Very good. I wanted to make sure that you realize once the angle got close together so that you can't resolve it, they just appear as one. You know how you guys look up at night and you look at all those twinkling stars? Here's a fun fact. Roughly 50% of all the stars you see in the sky are actually binaries. Binaries are really common for stars. Hell, if our planet Jupiter had been like 80 times more massive randomly, it probably would have formed a star and we would be in a binary star system. And we'd be looking at twin sunsets, just like Luke Skywalker in Star Wars.
So gas giants are basically the same thing as stars are. They just didn't have enough mass.
For fusion, right. Okay, does everyone have this? Because we got one left to go. I'm trying to get us through this because I know people have work and stuff. All right, I'm erasing. Chapter 6, number 54. Philemon, have you got that handy?
Yeah.
Okay.
Size of radio telescopes. What is the diffraction limit of the 100-meter radio telescope observing radio waves with a wavelength of 21 centimeters?
Okay. Let's draw a picture of what's going on. Let me show you a picture. You may not realize this, but radio telescopes do not look at all like optical telescopes. They look like giant radar dishes. Let's look at the Effelsberg radio telescope, which I think is also 100 meters. This is probably the telescope that they're referring to in this problem. Look at that beast, 100 meters in diameter. That's like bigger than a football field, right? That's huge. And it's a big radio dish. Now, you might think at first that radio telescopes are big because radio waves have a long wavelength, but that turns out to not be the case. You can build a radio dish of any size. Have you guys ever seen those little radio dishes that people have for like, what kind of TV? It's for satellite TV on the sides of your grandpappy's house? Those are actually little mini radio telescopes, and they can detect wavelengths of 1 meter or more easily. The reason why radio telescopes have to be large is because of something called diffraction. So let's just draw a picture and see what's going on. First, let's draw our radio dish, okay? So here's our radio telescope. The dish collects the light just like a lens or a mirror does. And then they have these things, these support structures, and attached to it is called a feed horn. The feed horn is what captures the radio light. And then you've got some kind of tower on which the thing stands, right? So here's your support structure. So we know that this dish is 100 meters in diameter. Now in comes a big ass radio wave. Since it's on the red end of the spectrum, I'll make my radio wave red. And the radio wave will be captured by the dish, and it will bounce into your feed horn, where the technician will analyze the signal. The reason why they're making them so big is because of something called the diffraction limit. And I'm also going to use alpha for diffraction limit because it's an angle, but I'm going to call it alpha min. The diffraction limit is the smallest angle you can see with a telescope of size D at wavelength lambda. For instance, in our previous problem, the diffraction limit of the Hubble Space Telescope is 0.05 arcseconds. So Hubble can see down to a minimum angle of 50 milliarcseconds. The formula for diffraction limit is very easy. It's the minimum angle that I can see is 250,000 arcseconds times the wavelength divided by the diameter. In this problem, they've given the wavelength as 21 centimeters. Once again, wavelength and diameter, they need to have the same units. Let's see if we can convert the wavelength to meters. The wavelength is 21 centimeters. Who knows the conversion factor?
100 centimeters per 1 meter.
Centimeters. And here's a totally not subtle hint.
Good thing I've been using metric system all my life.
Okay, Vlad, what do we got?
0.21 meters, because I'm from Russia.
Hold on, you got to go slower here. Everyone needs to see the conversion first.
So it's 1 meter over 100 centimeters.
That's right. It might be very easy for you, but I'll tell you, Vladimir, growing up in the US, I don't know if you've spent your entire childhood here, but when
No,
you don't
I actually arrived here when I was 14.
Oh, 14. So yeah, so you did spend a pretty impressionable part of your life across the pond, shall we say. And let me tell you, if you don't grow up thinking in terms of metric system, it can seem a little weird to some of these guys. It seems so logical and obvious once you're experienced with it, but it can seem very weird for the rest of these guys. All right, now let's plug it into our formula, okay? The minimum angle is 250,000 arcseconds times 0.21 meters over 100 meters. That should be a pretty quick calculation for you guys. Two sig figs. Well, Philemon, what'd you get? I call on you.
I keep getting 525.
Sure. Shall we round it to 530?
I got that too.
What are the units? Philemon, let's do some dimensional analysis here. What cancels?
Meters, arc seconds. Or
Right.
meters cancel. Arc seconds.
Meters cancel, arc seconds are left, right?
Yes.
Okay, who's good at dimensional analysis? How many arc minutes is that? What's the conversion to arc minutes?
So it's 1 arc minute per 60 arc seconds.
So how many arc minutes is that?
8.8.
9 arc minutes. Here's a thought. What's the angular size of the moon in arc minutes?
Oh,
What's the-
30.
Yeah. If it's 0.5 degrees, then the moon is roughly 30 arc minutes. Vladimir, 1 pixel on that radio telescope is 9 arc minutes. Do you see how crazy that is?
Wow, wow.
Let me show you what a picture of the moon would look like if you took it with the Effelsberg radio telescope. It would be roughly 3 pixels tall and roughly 3 pixels wide. That's what a picture of the moon would look like with the Effelsberg radio telescope. Because each pixel
Is that even a circle?
No, because each pixel is only is close to 10 arc minutes. So you'd sample 1 pixel, 2 pixel, 3 pixels across, and 3 pixels wide. That's what the moon would look like if you took a picture of it. That's how shitty it is. That's even worse than your 8-bit Nintendo games, you know? Why would you use or build such a potent radio telescope when its angular resolution is so crappy? Well, first of all, what you're trying to do is, because the angle goes down as the dish size goes up, you try to make your radio dish as big as possible so you can try to make your pixels smaller. But even still, radio waves are so long wavelength that the resolution is crappy. The thing is, you can see things with radio telescopes that you can't see with any other type of telescope. This reason, if you look at the old radio maps, let's look at a 21 centimeter radio map of a galaxy. In recent years, they've started to get more high resolution. But when I grew up in astronomy, this is what pictures of galaxies would look like in radio telescopes. They're so low resolution that you basically see, okay, there's kind of a spiral there, but you can't see like any of the fine details. It's all these big blocky blobs because you've got such crappy angular resolution. And yet you still do it. You still put up with this kind of, like, look, check this out. Here's a side-by-side picture of a galaxy seen, a photo negative seen in the optical. You can see these galaxies. And then here it is using a radio telescope. It's a much crappier picture with lower resolution. But it turns out that radio telescopes can see the cold gas. That's why they're interesting. Now, Philemon, what was the follow-up question that they asked? They asked 2 follow-up questions.
Yeah, compare this to the diffraction limit of the Hubble Space Telescope for visible light.
So let's just do that first. If we do 530 arc seconds divided by Hubble's 0.05 arc seconds, that basically gives you 11,000 times worse than Hubble. Where I did the calculation for you just to speed shit up. And what was the last follow-up question?
Explain why the radio telescopes have to be so big to be useful.
All right, so here's the idea. Radio wavelengths, I'm going to put this in really dumb words. Radio wavelengths are long, which leads to poor angular resolution. By increasing the size of the dish, we lower the diffraction limit underline diffraction limit because that's and add one more sentence at the bottom if you can see it here. And improve image quality. I don't know if that makes sense to you guys, but we can talk about it more at future classes. Basically, the bigger this number, the smaller that number. We covered a lot of ground today, and we had fun doing it, I think, although it was a little bit choppy, so I'm sorry about that. Let's just chalk it up to me being distracted by the Perseverance landing on Mars. That must be what's going on. That.
Do you mind lowering the camera?
Oh.
I didn't get the last sentence.
Sorry, Taryn.
Okay, all set.
Okay. Okay, so I'm sorry this went on for so long. I really got thrown off my horse when the power plug came undone. It took me a very long time to reboot, and that just screwed up my whole day. So these kinds of things happen sometimes. Thanks for putting up with me and suffering through the whole thing. We'll get through this. Next week, we are supposed to start the sun. I'm torn. Part of me wants to get going and talking about the sun so we can get into cool astro stuff. Part of me thinks we could probably use another day to talk about light and radiation. I think my plan is going to be to do Tuesday, we'll talk about light and radiation. Thursday, we're going to do a little bit of sun stuff. And we'll have a lab next week, but instead of homework next week, I think I'm going to give you guys practice problems for the test. Have we talked about that? Rather than do another homework, I think it would be better for us to spend our office hours doing problems that are almost identical to the ones that'll be on the test, but we can kind of practice it before we go into it so we can kind of train ourselves. Would you guys appreciate that? Would that be something you'd like to make use of? Okay.
Yes, please.
So I built that in. So I think that will be very helpful because then we can kind of say, all right, suppose I ask you this, which I'm going to ask you that with just slightly different numbers. How would you solve this problem? You can kind of try it out with me before you have to do it on your own. I think that'll be really helpful for you guys. Mateus, you went through this in the last class. Did you find that session helpful? Yeah. So don't take my word for it. Mateus says so, and Andrew did it too. So, all right. That's the plan. Take care, guys, and I will see you next Tuesday. Check out that Mars landing if you have the time, okay? Ciao.